With the recent Hurricane Milton hitting Florida and Hurricane Helene hitting North Carolina, for this episode of Engineering Academy, we'll be looking into what engineering projects we can do to minimize the damage of hurricanes and see if they are worth the cost. But before we do that, let's look into how hurricanes are formed. A hurricane, also known as a tropical cyclone or typhoon in other parts of the world, is a powerful and complex weather system that develops over warm ocean waters. Understanding how a hurricane forms involves a series of meteorological processes driven by heat, moisture, and atmospheric conditions. Here's a quick look at how hurricanes are formed. Hurricanes form over tropical and subtropical ocean waters, where the sea surface temperature, or SST, is at least 26.5 degrees Celsius, or 80 degrees Fahrenheit. This warm water provides the necessary heat and moisture for the storm system to grow. Hurricanes typically form between latitudes of 5 degrees and 20 degrees north or south of the equator, where the ocean is warm enough to support them. The formation of a hurricane begins with a pre-existing atmospheric disturbance. This disturbance is usually a low-pressure system, a tropical wave, or remnants of another weather system that starts the process of storm development. The disturbance creates a region of relatively low pressure in the atmosphere. As the warm, moist air over the ocean rises, it cools and condenses, releasing latent heat. This process drives strong convection, which refers to the upward movement of warm air. The condensation of water vapor into clouds releases more heat, further fueling the convection process. As more warm air rises, it causes air at the surface to rush in, forming strong winds. The Coriolis effect, caused by the Earth's rotation, plays a crucial role in the formation of hurricanes. It gives the storm system its characteristic rotating structure. In the northern hemisphere, the Coriolis effect causes hurricanes to rotate counterclockwise, while in the southern hemisphere, they rotate clockwise. The Coriolis effect is weakest at the equator and strengthens as you move towards the poles, which is why hurricanes don't form close to the equator despite the warm water. As the warm, moist air rises and cools, more air is drawn in from the surrounding environment to replace it. This creates a low-pressure center at the surface. As more air is pulled into the system and rises, the central pressure continues to drop. This pressure drop enhances the inflow of moist air and the storm begins to intensify. Once the system intensifies, the air starts to spiral inward towards the low pressure center. In the most intense storms, a well-defined eye forms at the center of the hurricane, surrounded by the eye wall, the most violent part of the storm, where the winds are strongest and the rainfall is the heaviest. The eye is typically a calmer, clear area at the center of the storm, ranging from 20 to 40 miles in diameter. It forms because air at the center is sinking, creating a relatively cloud-free zone. As the system grows, a feedback loop is established. The hurricane intensifies because warm, moist air continues to feed into the storm from the ocean surface. Rising air in the system condenses, releasing more latent heat, which powers the storm further, and the air pressure in the center of the storm drops further, causing the winds to spiral faster. This cycle continues as long as the storm remains over warm waters and specific atmospheric conditions. Hurricanes are categorized based on the Saffir-Simpson scale, which classifies them according to wind speed. A Category 1 hurricane is 119 to 153 kilometers per hour. Category 2 is 154 to 177. Category 3 is 178 to 208. Category 4 is 209 to 251. And Category 5 is 252 and greater. As the hurricane intensifies, it can increase in category with stronger winds, more rain, and a larger storm surge. Hurricanes are generally steered by large-scale winds, such as trade winds or westerlies. These winds push the hurricane in the direction that varies depending on the storm's location. In the Atlantic, for example, hurricanes often move westward towards the Caribbean or North America before being steered north or northeast by the westerlies. A hurricane naturally dissipates when it can no longer access the warm, moist air that fuels it. This occurs when the storm moves over land, cutting it off from its moisture source, or the ocean. The storm moves over cooler waters where sea surface temperatures drop below 26.5 degrees Celsius, or high wind shear, settling changes in wind speed and direction, disrupts the storm's vertical structure, causing it to weaken. As the hurricane weakens, its winds diminish and its well-defined eye can collapse, turning the system into a tropical storm or tropical depression. So what can we do to engineer a way to minimize the effect of hurricanes? To make it easier, we're going to look at ways to minimize the energy of the hurricane. First, we'll need to determine how much energy do we need to minimize. Total energy is the total wind energy plus the latent heat energy. Assuming 111 miles per hour, a radius of 500 kilometers, a height of troposphere is 15 kilometers, and the precipitable water is 0.05 meters, then the total energy we would need to dissipate would be equivalent to over 100,000 megatons of TNT. Alternatively, a tropical depression is only 10 to 15 megatons. So for all examples, we will assume we'll try to affect the hurricane in its earliest stage. Now let's look at 3 ways to do this. First, let's look at a way to cut off moisture from the ocean. A barrier or covering system that reduces or prevents water evaporation from the ocean could limit the moisture available to the hurricane. This could involve some form of floating reflective shields or vapor inhibiting materials spread over the ocean surface to prevent evaporation. Assuming a polyethylene cover that could cover the entire area of a hurricane, it would cost approximately $1 trillion just in the cover and weigh approximately 67 million metric tons. Stabilizing this cover would take specialized anchors and ships to deploy it. There will be high risk of the giant cover being torn, and deploying the tarp would be challenging due to the large weight. Essentially, we'd be adding a pool cover to a section of the ocean to minimize evaporation into the atmosphere. Another option would be to cool the ocean surface. Since hurricanes are powered by warm water, typically above 26 degrees Celsius, a machine might work by cooling the ocean surface temperature beneath a hurricane. This could be done with massive systems that mix colder, deep ocean water with warmer surface water, potentially through large pumps or artificial upwelling systems. Luckily, that system already exists. An ocean thermal energy conversion, or OTEC system, generates energy by using the temperature difference between the warm surface water of the ocean and the cold, deep water. In this system, cold water is pumped from deep in the ocean, typically at depths of around 1,000 meters or more, to the surface. The cold water then interacts with a working fluid, causing it to condense and release heat. This process can be used to produce electricity. Though these systems are still experimental, these systems at the scale to affect a hurricane are estimated to cost over $2.6 trillion to make any meaningful change in the hurricane's effect. The last area we'll look at is disrupting airflow. To disrupt the atmospheric processes that allow the humid air to rise and condense into storm clouds by creating artificial disturbances in the airflow through the use of drones. They could potentially interfere with the formation of the towering clouds that drive the hurricanes. In order to make this a reality, a swarm of drones would need to be at a great enough size to counteract the energy of the hurricane. A rough calculation of one drone every square meter of the hurricane would be needed. Therefore, a minimum of 725,000 drones would need to be in our example. Assuming $600 per drone, then it would cost over $430 million. Coordination software in order to swarm in a synchronized manner and other required upgrades would most likely take an additional $300 million. Hurricane Helene in North Carolina is estimated to have caused over $200 billion in damage. Even if the estimated cost of building solutions to minimize the effect of hurricanes is $1 trillion, it is worth the investment to avoid these catastrophic events from occurring. The international community should sponsor engineering feasibility studies like these in an effort to have a valid response to future hurricanes. Hope you enjoyed this episode of Engineering Academy. If you have any other ideas, please let us know in the comments section. Have a great week, and don't forget to never stop learning.